So for this particular RC problem, you are given that the electromotive force of the circuit is 100 volts and the resistance is 5 ohms and the capacitance is 0.02 farad. Now initially, for this particular capacitor, since it's an RC circuit, we have 10 coulombs as the charge. Now find the current in the circuit at any time t and find the charge at any time t as well. So we have two unknowns, the current and the Q, the I and the Q for this particular circuit. So we are to account for it at any particular time. Now your EMF here is a constant voltage source. So it's a constant voltage source such that it is labeled as B sub S, a constant or a steady state voltage source. Whenever you see an EMF which is a constant, then your circuit is a DC circuit. The current is supplied through the battery or from the battery. So our battery in this case is 100 volts, so it's constant. Now if we are to use the laws of Kirchhoff's and we will sum up all the voltages in our circuits, the voltage drop in each of your elements in this circuit, that is the resistor and the capacitor, should be equal to the steady state, or shall I say the electromotive force, which is a constant, or the constant voltage source, which is 100 volts. Now for our resistor, we know that our voltage drop is equal to IR. So last week, or that's 2 weeks ago, it's IR, and in here we have replaced the I by an equivalent expression, which is the derivative of the charge passing through the derivative of the charge with respect to time, or this is the rate in which the charge in your capacitor is changing. So we change the I into this expression. That way we can find an equation in terms of the charge in the capacitor. Why do that? Because our problem gives us the charge initially in our circuits. So the problem did not give us the current we can place in here. So we might as well change the current into its equivalent expression in terms of the derivative of Q with respect to time. As for the voltage drop across our capacitor, so you have learned that as well 2 weeks ago, and that's your Q over C. The charge in the capacitor divided by the capacitance. And again, we have copied what is on the right side of the equation, which is V sub S. Now, if we will write this particular original DE in the second line into a DE wherein the unknown function is specified and the independent variable as well is clearly written, then it would be something like this. We divided the original DE by R. So the denominator now of the second term here will have R, the same thing with the only term on the right side of the equation, which is also having a denominator of R. If you look very closely, this DE is linear. And it is a requirement that if your DE is linear, you are to determine the integrating factor, which is equal to E raised to F of T, or in this case, that would be P of T. This is our P of T, 1 over RC, and this is our Q of T. So if you do that and you process the formula in determining the solution of a linear differential equation, I'd like to go straight to what we have in here. The answer would be something like this. So when we write the response of an RC circuit in terms of the charge, this will be our equation. So we write the response again in terms of the charge because the problem gives us or gave us the charge. The problem did not give us the amount of current because it's the thing that we're looking for. So that's it. So this is our response in terms of the charge. Now, since we know that the voltage drop across the capacitor is Q over C, we can change this Q in terms of V, C, and C. So in that case, you will have an equation now in terms of the capacitor voltage. You see this particular subscript C on the voltage that represents the voltage drop across your capacitor, or simply the capacitor voltage. So the response in this equation can be written in terms of the charge and in terms of the capacitor voltage. So what's done in here is we have replaced the Q by C VC and divide the entire formula that we have on top by if in order for us to only have BC here, we will need to divide the entire equation that we have here by C. So that is why the C is gone in here. And by the way, this would be K over C here. I missed writing it down. So if this is K E T negative T over RC, and if we change this Q here to BC, B sub C times C, then there's a need for us to divide this entire equation on the right by C. And the C is not written here. So there should be, the first term class should be a K over C, E raised to negative T over RC plus V sub S. So the C here is gone by the division of the C. So if we will substitute the given in the problem, and that's our constant voltage source of 100 volts, our resistance of 5 ohms, and our capacitance of 0.02 farad in our equation, we will have Q equal to K E raised to negative 10 raised to T plus 2. At time equal to 0, your Q sub O is 10 coulombs. It's stated in the problem that initially the charge in the capacitor is 10 coulombs. So if you substitute the T here, which is 0, and you have 10 in here, you will have a value of K, which is equal to 8. In this case, class, this K here should be K over C. So there should be a change in here. This 8 is K over C. So if really only want the K, this 8, the 8 that you have here should be multiplied by the capacitance given in the problem, which is 0.02 farad. Okay, so there's something that needs to be edited here. This one should be K over C, and as such your K will be 8C, and as such the actual value will be 8 times 0.02. So your actual equation for the charge at any particular time in your capacitor having a unit of coulombs will be 8 over C. So this should be 8 over C, whatever that C is as given in the problem, which is 0.02, E raised to negative 10T plus 2. So where is this coming from? Actually, it came from this one wherein we already substituted the K, which is 8 in here. But that should be 8 times C in this case. So for the current, in this case, you have it as equivalent to the derivative of the Q with respect to time. And since you already have the equation for the Q, this is your equation for the Q, it will solve the charge in your capacitor given the time in seconds, and the unit will be in coulombs. What you're going to do is just differentiate your answer here. So your answer, this answer should be differentiated, and that should give you the current in the circuit at any particular time. So as to the final answer to this problem, your Q at any particular time will be 8 over C. Again, there should be a C, E raised to negative 10T plus 2. And your current is taken from the Q, which is equal to negative 80 E raised to negative 10T. So being current, then it has a unit of amperes. There's something you need to know about this one. So the negative sign that you are seeing here, due to the derivation that we have for the E raised to U, and the derivative of such is negative 10 for the U. So that is why this became negative 80. So the negative sign simply means that the current reverses its direction. So the assumed direction of the current is actually not the correct direction in which it is flowing through your circuit elements. So nothing to worry about the sign. It's just the direction that it is representing. So if it's negative, then it's the opposite of the assumed direction. Now, in RC circuit, so we're talking about an RC circuit here because we have a resistor and a capacitor. The capacitor voltage is generally the desired variable. So that is why we have this particular equation that allows us to solve for the charge in the capacitor. If it's the RL circuit, it is the inductor current that is the desired variable. So one thing that you should know about the RC circuit is your equation for the voltage in the capacitor, because most of the time it is the desired variable. If you're talking about the RL circuit, it is the inductor current that is often being asked by the problem. So if this is our equation for the voltage drop across your capacitor, so you have this formula, and if we will determine the voltage across it initially, so that would be at time equal to 0, all you have to do is substitute the values that you have for time here equal to 0, and that would give you a value which is 500 volts. So at t equal to 0, the k, however, the k value is not the correct k value here. That's 8, so this should be 8c. And then this would be e raised to negative 10 times 0. So that would be e raised to 0, which is 1 plus 100. So this should give you a VC, which is 500 in here without the correction. But if you have the correction reflected, of course, it would not be the answer. So you have here the 500 and you have k e raised to 0 plus 100. The purpose of this is for you to know the constant k. What is the value of the constant k if you substitute here? So we have the answer to be VC equal to 400, because we already determined the 400, e raised to negative 10t plus 100 plus 100. The entire equation has a unit of volts. Now, any questions so far? Any question? How we got the 400? How we got the 500? Any question? By the way, class, this one, since you're not asking, the VC that you have substituted here was computed based on the formula Q over C. And since we want to know initially the value of the VC so that we can substitute it in this equation on the left side with a time equal to 0 here, so that we will know the K, then you have to substitute, since this is time 0, you have to substitute for the charge in your capacitor, the 10 coulombs that was stated in the problem. So initially, the capacitor has a charge of 10 coulombs. If you divided that by 0.02, then your initial voltage in your capacitor is 500. So initial, meaning that's a time equal to 0. The purpose is just for us to know the K. So as for the formula that will allow you to solve for the voltage across your capacitor given the time, which is greater than 0, the formula is this. 400 e raised to negative 10t plus 100. However, class, this formula is only true for the circuit that we're talking about, because the values that we are substituting is only true for that particular circuit. If it's a different circuit, our equation will be different. Our equation will still be this, but of course we will have a different V sub S, and we will have a different RC, and we will have a different K for that matter, which we will place in here. But the general formula is this one. If we would like to check, the current in the capacitor is equal to C times the derivative of the rate of change of the VC dt. So if you do that, this is your equation for the VC. So if you're going to differentiate it with respect to time, the current is still negative 80 e raised to negative 10t. So this is another method of determining the current, which was already determined here. Okay. Now this is one method that you can use in determining what is required. That's the Q and the I. And another method in determining the I is this one. Based on the fact that it's commonly required, or it's commonly the required unknown for RC circuit, that we know the voltage in your capacitor or the voltage drop in your capacitor. So finding the I in this case is based on the voltage drop in the capacitor. So you have this formula. The current in your capacitor is equal to C times the rate of change of the voltage drop in your capacitor. So you're knowing something again in here. Okay? So you still have the formula for the current and the charge. So that's the main thing that is being asked by the problem here. The current and the charge in your capacitor at any time. So this is for an RC circuit. Okay. Now, the current can also be obtained directly using the KVL equation. So the KVL equation, the main equation that is being used in circuit, voltage drop across circuit elements equal to the electromotive force. And we have VC equal to Q over C, and I is dQ dt. So it follows that your Q, if we treat this as a separable dE, will be the integral of I dt, which will tell us, therefore, that your voltage drop across the resistor, which is Ri, plus the VC, which we will change to Q, which is the integral of I dt and divided by C, because our V sub C is Q over C and Q is this, equal to Vs. And this is an integral equation. So if we will process this one by differentiating both sides of the equation, if you differentiate both sides of the equation, then you will have the derivative of I with respect to time, and the derivative of this will be simply the I, and the derivative of a constant will be a 0. Then we will divide the entire line or the entire equation by R, and we have this. And our I, in this case, is K e raised to negative T over RC. How do we define, or how did we get the I? This could be treated as a separable differential equation. Transfer this one on the other side, and the dt also on the other side. The I will be in here. This should give you the equation. You will have an ln of I, which will require you to raise the, or make the terms in your left side and right side of your equation the exponent of the E. That is why you already have the appearance of the E. In this case, if you will substitute what is given in the problem, you will have I equal to K e raised to negative 10t. And again, we have this. We have already determined this a while ago, that our charge in the capacitor, or rather our voltage drop in the capacitor at time equal to 0 is 500. So your I of 0, that's initial current in the circuit, will be 100 minus 500 divided by 5. And that's negative 80. Remember, class, that your voltage in your capacitor, rather in your circuit initially, is 100, because this is your constant voltage source. And this is now the voltage initially at time equal to 0, 500. So the 100 minus the 500 over 5, this 5 is the, what is this 5, by the way, that you see in here being divided? Where did this 5 came from? 100 minus 500 divided by 5. So where did the 5 came from? So based on our given, the 5 is the resistance. Okay, that's the resistance of your resistor. So what's happening here is your V sub S minus VC divided by the R is the current in your circuit at time equal to 0, and that's 80. So what's done in here, it's plugged in here on the equation K. So negative 80 e raised to negative 10t. Now, this is in the case, there's just so many things in here because this is a detailed discussion shared to us by Dr. Lumanang. So this one is a circuit wherein your EMF is a constant. You have a constant voltage source and it's 100 volts. Actually, the challenge is even more, or it's more of a challenge if your EMF is not anymore a constant in the case of an AC circuit. So in the sample problem here, in the second sample problem, and I think I've given you a sample also similar to this, wherein the EMF is not a constant. So it's an AC circuit. So you have 400 cosine 2t, resistance of 100, and a capacitance of 0.01. Again, we are given the initial charge in the capacitor. The difference of this with sample problem number 1 is that your charge in the capacitor is 0. Now, just like number 1, you are to find the current in the circuit at any time t. So there's a note here that 400 cosine 2t is a sinusoidal AC voltage source. So I have mentioned that already. Again, KVL will give you this. Then you will have this equation. Then you will have this. I have already shown to you a while ago. And this one, if you substitute the R and the C for the denominator here, and the same thing with this one, you will have this equation, which is, of course, linear. And if it's linear, there's a need for you to find the integrating factor, and it's e raised to t. And I have given you a similar scenario also, that you have to integrate an exponential function together with a trigonometric function in this case. Now, you have here a more generic formula that will not lead you to do double integration by parts. That is, if you don't want to process it using double integration by parts. But this is already a pre-derived formula for double integration by parts. So in the formula, you just have to know what is the constant that appears in the exponential function, and that's c in here. And what's the constant in the argument of the cosine? So in that case, that would be 2 in here. Whenever you are given such an integral in terms of the pattern, which is similar to this, your answer readily will be this one. So all you have to do is affix the C and the B in the given formula in here. That way you won't have, as I said, to do double integration by parts. I think majority of you, probably Miss Niti, also shared this particular more direct formula in processing an integral. I normally don't give my students formulas that would readily give the answer unless I see that the students know where that particular formula or derived formula came from. So since you know already how to do double integration by parts, because it was given to you already more than a couple of times in the quiz and in the sample problem, which you studied before, then this is now that ready-made formula that you can use. I'm sure there is an equivalent formula for the sine for this one. Excuse me. For this one. So all you have to do is use that same formula as well. I don't mind you using the direct formula already. So if this particular DE is processed already coming from the linear differential equation, the final answer would look like this. Q is equal to K e raised to negative t plus 0.8 times this. That is if we have already used this one. Now, initially, there's no charge in the capacitor, so we will substitute Q0 here, T0, and 0 also in here. So cosine of 0 is 1. We know that. So we will have your Q at any particular time will be equal to negative 0.8 e raised to negative t plus all of this. Because we have already determined that K from this initial condition is equal to negative 0.8. This allows you to determine the current in our circuit at any particular, the charge in our capacitor at any particular time. Knowing the charge, then you know this already, then you can find the current by differentiating the equation that you have for the charge. So if you differentiate, this will be your I. I is equal to negative, or rather the negative sign now was already taken care of by the negative of the exponential function here, the negative argument of the exponential function. So this is now your current. If you look very closely, and I think I have mentioned this also, I have mentioned this, your current expression here has two sets of terms, the one that is exponential in form and the other one that is trigonometric in form. The other set, I mean, because you have the sine and the cosine. The one that is exponential in form is the natural or the source-free response. The natural, transient, or source-free response, and it's having a subscript of n. The last two terms, which has the trigonometric function sine and cosine, is referred to as the forced or steady state response. So just in case you would be asked, given a problem, what is the expression for the natural, transient, or source-free response? So for your RC circuit, that would be this one. And your forced steady state response is this. Okay? So this is under method 1, the crude procedure of finding the charge. You won't get lost with this particular fundamental principle because you've learned these things in physics, okay? The KVL. Now, another method is we can have this particular formula, though I don't suggest that you really have to like memorize everything, although you don't need to memorize everything because you can readily open your notes in your case now because you have everything which you can open during the quiz and the exam. You have this alternative formula to use in terms of the current in your RC circuit. So in here, you are given the form of the transient response, and in here is the form of the steady state response. You may wonder why this is not really equivalent to the one that we're seeing here, which has both the sine and the cosine. But actually, if you remembered your trigonometric identity, that whenever you have the sum of the cosine of two angles, this could be processed as cos minus sin, cos sin, with the two thing inside. So if you'll have this expanded, comparable to, it would look something like this. Okay, although this one is in the form of a cosine of the sum of two angles, but still it would be equivalent to this if you will have to expand it using the trigonometric identities. So in our problem, if you will given a 400 volt source and a radiant frequency of 2 radians per second with a resistance of 100 ohms, everything you can substitute in this formula for the Z. You need to find the Z which you need to place in here. So your Z is 111.803 ohms. Now look at this. Now you're learning a new term. This Z, which is the square root of R squared plus 1 over omega C quantity squared, is the impedance of your RC circuit. Okay? Just in case you would be asked again, what is the impedance? So it's just about the use of the correct formula and knowing what to substitute on the variables that appear in the formula. Okay, this is for the Z. As for the power factor angle, this is equivalent to controls later on when you reach in 4th year. This is equivalent to the phase lag, but in here in circuits, they refer to that as the power factor angle. So that would be the arctan of 1 over omega CR. Now this being radian values, you don't see any degree value here. We are expecting that the angle or this power factor angle will have a unit in radian as well, unless otherwise that your calculator is set on degree mode. So automatically your calculator will be the one that will give you the value in degrees. But I am suggesting that your calculator should be placed at all times in radian mode. You can readily convert it to degrees anyhow. We know that 180 degrees is equal to a pi radian. That way you will not get confused or lost when you do your computation. So your I in this case, based on this particular formula, using this and these two formulas, this one taken from the first term and this one taken from the second term, will be now this after substitution of the values that we got. And if we need to determine the K again initially in the circuit, we need to know the current. So the current in the circuit at time equal to 0 is this, 400 cosine T over 100. Or that's the V over the R. where did you get this? Means this is taken from the formula that the voltage drop in your resistor is equal to IR. So if you want the I, then that would be voltage over the R. And that's 4A, 4 amperes. This 4 amperes you substitute here. Your T here will be 0. Your T here will be 0. You get to know the K, which is zero point 0.8. And again, after knowing the K, which is 0.8, you go back here and substitute that one. So the two expressions that we have here and on top are identical, whether you use method 1 or method 2. Although the only added challenge in method 2 is for you to know that there is this such formula for determining the current in your RC circuit. And this formula already takes out the differential equation from the picture. By the way, this is already a ready-made formula, so there's no DE here that you are seeing. But just probably for you to know, and for you to know this thing about the impedance and the power factor angle, then I am sharing this to you. Our exam is departmentalized, so I don't want you to miss anything that the electrical engineering students know, and the ECE section also, the section which is 100% all ECE that they know in their circuit application. So these are things that you need to add to those that I have taught you already regarding RC circuit. Okay, so this is RC pa lang. I have actually added 4 files in Canvas. I'm sharing to you 4 files. All have sample problems on RC, RL, and the complete response of the circuit also for an RL circuit. Now, what about an RL circuit? If I will get disconnected, class, we will just reconnect. So I'll go to the next file here. So this time we have an RL circuit, and the EMF is constant and the resistance is 50 ohms, and you have the inductance of 1 Henry, no initial current. Again, the requirement is the current in the circuit at any time. Now, we have a constant voltage source. The value is 5 volts. So the current in our RL circuit, as already derived before, is K e raised to negative RLT plus Vs over R. This Vs is for your EMF, which is a constant. Now, at time equal to 0, the problem says that the current in the circuit is 0. So you substitute 0 here. The time here is 0, so you will have a K and you have Vs over R. It follows then that for your RL circuit with no current initially passing to your circuit element, that this is your current at any particular time. We just took the K constant value, which is negative Vs over R, and we just substituted it back on the original equation where it is not yet specified. So I place it in here. Then if we factor out the common in the two terms, which is V sub S over R, then this is our final formula. In our circuit, this is the final formula by